If I was to draw a picture for you of two objects, one object, number one, moving towards a stationary object, number two, let's say these two objects collide, head off as one object after the collision. We know how to analyze this, right? We know what to do. We'd say Pi is equal to Pf. We'd say M1 V1I plus, if object number two is at rest, we could say M2 V2I, or we could just say 0 equals, if they stick together, it would be MT times VF, right? Nothing new there. We've been doing that for a couple of days now. This is just a simple, straightforward collision. One object is at rest. They stick together. They head off as one. M1 V1I plus 0 equals MT times VF, right? All right. Well, what if we had something like this? What if we had object number one at rest and object number two moving down towards object number one? Let's say, once again, they stick together and they head off as one. Well, we know how to analyze this as well. For this one, we'd say Pi is equal to Pf. We'd say this time 0 plus M2 V2I equals MT times Vf. Agree? Object number one is at rest. It has an initial momentum of 0, so we'd say 0 plus the momentum of object 2. The only trick that we have with this one is that object number 2 is moving downward, so the initial velocity would be negative, right? That's the only real thing that could trip us up on this one as compared to the black one. What about this? What if we have a situation where object number 1 is moving to the right, and object number 2 is moving downward at the same time? Let's say they collide right here, and they stick together. Where is that wreckage, or whatever you want to call it, that mass, object 1 and 2 combined, where are they going to go after they collide at that point X? Yeah, it's going to go southeast somewhere, right? Going to go down here somewhere. If we have a downward momentum before the collision, well, then we have to have a downward momentum afterwards. If we have a rightward, is that a word? A rightward momentum before the collision, then we have to have a rightward momentum after the collision. So it's going to go right and down. How would we analyze it, though, mathematically? Well, go ahead.
You'd have a funny angle, so you'd have to calculate the horizontal.
Well, we would end up with a funny angle after we were done. Okay, this is the kind of thing where we'd be looking to solve for VF here. But we wouldn't deal with that funny angle, resolving it into its components in the beginning, because we wouldn't know what it was. That's what we were trying to find. We would treat this the same way as we treated problem number 1 and problem number 2. We would break this into an x component. The x component of this would be exactly the same as this. It's exactly the same problem. That is the x component. We're not done this third problem yet, right? But the part that we've just done is exactly the same as problem number 1 here. M1 V1I plus 0 is equal to M2, or M total, times VF. Why do we still have the 0 here? Why do we still say 0 right here? Yeah? Good. We're analyzing x component here. X is horizontal, right? Left, right. How much of object number 2 is moving horizontally? None. So what we're essentially doing with this third problem right now, while analyzing the x component, is treating it like this first problem. We're pretending nothing on the y-axis exists. So if we look at this third problem, pretending nothing on the y-axis exists, then object number 2 is effectively at rest. Now, let's go to the next step. Let's analyze the y component now. What would the y component look like? Exactly the same as the second problem. Now we would say 0 plus M2 V2I equals MT times VF. Why 0 to start off here? Well, because object number 1 is not moving on the y-axis. We're paying attention only to the y-axis now. So it becomes, if we're not looking at the x-axis, if we're ignoring everything on the x-axis, then it's just the same as the second problem. What do you think we do with this? We got an x component and a y component. Solve for VF, probably. Solve for VF for the x and VF for the y. That's usually what we end up solving for. What are we going to do with that? Add them? Yes. But how are we going to add them? Yeah, a triangle. We've got an x component. We've got an x component like this that we just solved for. We've got a y component like this that we've just solved for. And then we're going to combine them or add them by drawing a resultant vector from start to finish. Remember last year, Physics 20, when you're drawing vector diagrams? We always draw the components of the vector head to tail. Right, the head of one vector to the tail of the next vector. And then the resultant gets drawn from start to finish. It's exactly what we just did, right? Let's solve for VF here using the Pythagorean theorem. And let's solve for theta using the inverse tan function. Let's take a look at an example problem. 1,200 kilogram car traveling north at 10 meters per second collides with a 1,500 kilogram car traveling west at 12 meters per second. I'm going to draw this out. This is what you should do every single time you have a two-dimensional collision. We know it's two-dimensional because we get north and west. It's not north and south or east and west. It's north and west. Okay, whenever we have something like that, we want to draw this. So let's say, here's my 1,200 kilogram car. I'll make that car number 1. Doesn't really matter which one we call it, but 1,200 kilogram car traveling north at 10 meters per second. It collides with a 1,500 kilogram car traveling west. We'll call that one car number 2 at 12 meters per second. They strike each other, they collide, they entangle, and they head off as one after the collision. If we have an upward momentum before, then we have to have an upward momentum after. A left momentum before, we have to have a left momentum after. So we expect the wreckage to go left and up. And that red vector is what we want to find there. So we break it into x and y components. For the x component, pi is equal to pf. We're going to say what? What's the first term that I put in there? m1 v1i, but what's v1i? 0, because it's moving only in the y-axis and we're looking at x here. I'm just going to say 0 plus m2 v2i equals mt times vf. Does that make sense? Does that make sense? Kinda?
I just wrote down the opposite way in my notes. I had x as
Oh, I see. So you call this one number 1 and this one number 2?
yes. I just went by x's in place of my notes.
Okay. Doesn't matter which one is object 1, which one is object 2, but if you reverse the order of it from what I have here, then you're going to say m1 v1i plus 0, right, as opposed to 0 plus m2 v2i. Bottom line is this blue one doesn't have any x component to it. It's this whole 10 meters per second is all on the y-axis. So say it's 0 here. Okay, let's sub in some numbers here. M2 is 1,500 kilograms. It's times negative 12 equals 2,700 kilograms times VF. When we multiply 1,500 times negative 12 divided by 2,700, we end up getting a VF here of negative 6.66667 meters per second. Write down the unrounded number because it's not a final answer. What we just found is the x component of my final answer. Now, the y component. We're going to say again, pi is equal to pf. We always do this for a collision, right? We're just doing it twice this time because we have an x and a y. We're going to say for the y component, m1 v1i plus, Aiden? m1 v1i plus m2 v2i, but what's v2i? 0, right? Okay, object number 2 is only on the x-axis, and we're looking at the y-axis right now. So I'm just going to put in 0 because I know that m2 v2i is 0. Equals mt times vf. m1 is 1200 times positive 10 equals 2700 times vf. When we multiply 1200 times 10 divided by 2700, we end up with a vf equal to positive 4.444 meters per second. Now what do we do? By the way, what have I just solved for? The y component of my final answer. Now what? Now what? Yeah. Let's draw a vector diagram here. We have 6.66 to the left. We have 4.44 upward. We know it's left because it's negative. We know it's upward because it's positive. And we're going to find the resultant vector by doing the Pythagorean theorem. A squared plus b squared equals c squared. We end up getting 8.01 or 8.0 meters per second at an angle of, say it's the inverse tan of opposite over adjacent, at an angle of, make sure you're in degree mode here, 4.44 divided by 6.67. 34 degrees, and that 34 degrees would be north of west. We're measuring that from the west axis, and it goes north from that. So north of west. Okay, I'm going to get you to take a look at worksheet number 4. Right now, for the time being, I'm only going to have you work on questions 1 to 3 on worksheet number 4, please. I want to take a look at example number 2 now, which is similar to, but yet different from, example number 1. This one says a 3-kilogram bundle of fireworks sitting on a table explodes into 3 pieces. First piece, mass 1.2 kilograms, goes directly north. Second piece goes 30 degrees south of east. What's the velocity of the third piece? This is conservation of momentum as well, right? Every time we have an explosion, every time, always, we think conservation of momentum. Let's draw a picture. Okay, as I was walking around, as you guys were working on the worksheet, it's amazing how many people think they're smarter than they really are. It's amazing how many people think, no, I don't mean that as a knock because I'm not smarter than, well, you know what I'm trying to say. Maybe. I was confusing myself there. See? I'm not that smart either because I was confusing myself. As I'm walking around, people are skipping the diagram. I don't need to draw a diagram. I'm smarter than that. No, you're not. You need to draw a diagram. Okay? All of you need to draw a diagram for these questions. All of you. People are skipping steps. It's like, yeah, you know what? Sometimes you get the right answer by skipping steps, but not always. We want the right answer all the time, not some of the time. First thing we're going to do with this question, as with every other two-dimensional question, is draw a picture every single time. This X represents my explosion point. I've got 3 pieces after the explosion going off. The first piece goes directly north, so we'll say this is object number 1, 1.20 kilograms, and it's going at 120 meters per second. We've got object number 2 going at south of east, 30 degrees right here. Okay, that's measured from the east, south from the east. It's going off at 100 meters per second, and it's going with the mass of 1.10 kilograms. We got a third piece going somewhere. Where do you think that third piece is going to go? Probably down and to the left here. We don't know that for sure, though. We know for sure that it's going to go left. We have a total rightward momentum initially. We have to have, rightward momentum due to object 1 and 2. We have to have a leftward momentum to counter that. But as far as up and down goes, we have up and down with object 1 and 2. It depends upon which y component is bigger. We don't know which way object number 3 is going to go as far as the vertical axis goes. But you know what? If I draw it going down and left and it's really going up and left, that's not really a big deal. Okay, I'm just drawing it this way to help me visualize it. Okay, if it happens to be up and left, then my visualization was off a bit, but that's not the end of the world. Okay, what do you think is coming next? What do you think is coming next? The very next thing that I'm going to do here. Nope. Well, kinda. Result? No. Before conservation. Yep. Deal with the funny angle. Right? Look at our list here of always, our always list here. We don't like funny angles. That's the very first thing on our list here. Got a funny angle? Deal with it. Let's take it off to the side over here and get rid of it, turn it into X and a Y. We've got 30 degrees right here. We've got 100 meters per second. Let's change that into an X and a Y. We're going to say for the X component, because that's the adjacent side, cosine 30 degrees is equal to adjacent over hypotenuse, or X is equal to 86.6 meters per second. And we're going to say sine 30 degrees for the Y component is equal to opposite over hypotenuse, and Y ends up being equal to 50 meters per second. So I've just resolved this funny angle 30 degrees into an X and a Y. Now, what I'm going to do here now, you don't have to do this. It's easier for me to do this because I can erase really easily and erase and replace. Okay, what I'm going to do is completely get rid of that arrow that I just drew, and I'm going to draw this now as 86.6 and 50. I'm just replacing that one arrow, that 100 meters per second at 30 degrees, with an 86.6 to the right and a 50 downward. If you don't redraw it like that, at the very least, picture in your mind the new diagram like that. Well, now I do X and Y components. Now I'm going to say the X component, Pi equals Pf. Hey, what is the initial momentum of this? Bomb? Or what, was it a bomb? Firework? Same thing, yeah. Firework is just a little bomb. What's the initial momentum of it? 0, because it's at rest. If it was moving, then we'd have to put an mt times v term in there, right? But it's not. So 0 initial momentum. The final momentum is, how many objects do we have afterwards? 3. So it's m1 v1f plus m2 v2f plus m3 v3f. We wish the masses of the pieces were the same so we could cancel them, but they're not. It's not a big deal. Object number 1 has 0 momentum. How come? Because what? Because what, Aiden? Because it's going up, and we're analyzing the X component here. Good. Object number 2 has a mass of 1.10 kilograms times a velocity of, what is it, Kennedy? 86.6. Right, the X component. It's easy for us to visualize that 86 now because of the way that I have that drawn, right? M3 is, oh, we don't know what M3 is. Anybody? The total mass was 3 kilograms. 1.2 went one way, 1.1 went the other way. What's left? 0.7. times V3F. Let's find V3F. Gives us negative 136.086. Right, 1.1 times 86, take it over by subtracting, divide by 0.7, get negative 136. Hey, guess what? My x component, I said was negative. We drew it to the left. Does that agree? Yeah, I said that it was going to go to the left. I got a negative value for the x component. I guessed right. Well, it wasn't really a guess, right? We knew it was going to go to the left. Our issue was the up-down component of it, right? Let's take a look at that y component now. Pi is equal to Pf again. What's the initial momentum for the y-axis? 0. It's at rest. It's for the y-axis as well as the x-axis. Equals m1 v1f plus m2 v2f plus m3 v3f. What's v1f? What's v1f for the y-axis? 1.2. So we're going to say, or 120 I should say. So we're going to say it's 1.20 for the mass, 120 for the velocity. The second mass is 1.10. What's v2f? What's v2f, Kenny? 50? Close. Negative 50 because it's down, right? Negative 50. Right, Luke? It's easier for us to visualize this if we have it drawn like we have it drawn there, right? Negative 50 on the y-axis. Negative because it's downward. Plus M3, 0.70 kilograms times V3F. Solve for V3F here. You end up getting negative 127. Anybody else get that? Negative 127? Okay, I kind of guessed that it was, I knew it was left. I kind of guessed that it was down. Is it down? Did I guess right? Yeah, it's left because it's negative 136. It's down because it's negative 127. Now what? Now it's physics 20. And guess what? You all passed physics 20. All of you. So we know what to do here now. We got negative 136. We have, what was that, 127? And we're going to find the resultant vector by doing the Pythagorean theorem. Draw your arrows. Don't skip arrows. Okay, your component vectors have to be drawn head to tail. Your resultant vectors drawn from start to finish. Solve for v, solve for theta using the inverse tan function exactly like we did in the last question.